So if anybody new that's joining us, this is the Tissue Image Analytics Center seminar series. This is going to be the final seminar of the semester, so for the autumn-winter semester. And today we have Çiğdem Gündüz Demir joining us, who'll be giving a presentation on segmentation networks in digital pathology. So Çiğdem received her bachelor's and master's degrees in computer engineering in Turkey in 1999 and 2001 respectively, and her PhD in New York in 2005. And Çiğdem is currently a professor of computer engineering and the associate director of KUIS AI Center at Koç University. Before joining Koç University, she was working as a faculty member at the computer engineering department at Bilkent University, where she was a visiting professor at Nanyang Technological University, NTU, in Singapore, also in autumn 2009, and Stanford University in spring 2013. Çiğdem's main research interests and projects include development of new computational methods based on deep learning and computer vision for medical image analysis. And currently her research group works on the interdisciplinary projects and collaborations with departments of pathology and biology for the microscopic analysis of histopathological images and in vitro fluorescence and live cell images, and with the departments of ophthalmology and radiology for the analysis of images acquired with in vivo imaging of CT, MR, and OCT. So finally, Çiğdem was a recipient of the Distinguished Young Scientist of the Turkish Academy of Sciences and Career Award of the National Scientific and Technological Research Council of Turkey. So hopefully I've given a good introduction for you there, Çiğdem.
Thank you very much. Thank you very much for the nice introduction.
No problem at all. So anybody on the call that has any questions during the presentation, please feel free to raise your hand or type in the chat window. So with that, you can start your presentation whenever you are ready.
You need to give me the right for sharing my screen.
I do.
Okay.
Okay, hopefully now you'll be able to share your screen.
Okay, just a second. So let me check my presentation. So let me try to. Just a second.
That's fine.
Thank you. Okay, sorry.
Completely
okay.
fine.
Thank you very much once again for your nice introduction. So I am very happy to be here with you today. I am Çiğdem Gündüz Demir from Koç University. I am a faculty member at the Department of Computer Engineering, and I am also the Deputy Director of the Artificial Intelligence Center at Koç University, which is a leading academic institute of AI in Turkey. So let me first start with telling you where we are physically located. So we are in Turkey, we are in Istanbul, we are in the northern part of Istanbul, where Bosphorus merges the Black Sea. These are the university buildings. This is our campus. So we have a very nice campus. It has a spectacular view. We are in the forest. We can see both the Bosphorus and the Black Sea from campus. So you're always welcome to visit us, visit our campus and visit our center. And I will be very happy to host you at Koç University. And this is our Artificial Intelligence Center, AI Center. It is located in the engineering building. And we are a young research center, which was founded at the beginning of 2020 with the donation of İşbank, which is one of the biggest banks in Turkey. We are currently 15 faculty members from different departments working on different aspects of AI. We have also 30 plus affiliated faculty from different schools, School of Medicine, School of Law, School of Social Sciences, with whom we are working on interdisciplinary projects. At the center, we have more than 100 graduate students, and this number is growing. So we have also a nice floor in that building. It is in the financial district of Istanbul, where the headquarters of İşbank is located. So we have a very lovely working environment both on campus and in the city. And at the center, I am leading a research group on medical image analysis. Together with my students, we are working on the design and implementation of computational tools to automatically analyze images for medicine and biology research. Our current focus is to develop deep learning models. Our university has also a very strong medical school, and we are collaborating with many professors from our medical school. Do we have a question? Okay, feel free. Okay, that is Simon, that's you. Okay, so we are closely collaborating with the medical doctors. So I will be talking about our collaborative work on digital pathology in the next slides. But besides that, we have collaborations with the departments of radiology and anatomy, and also with the Department of Ophthalmology on CT scan analysis and optical coherence tomography image analysis. Additionally, we have strong collaborations with the biologists on nucleus detection and segmentation problems, but in vitro images, these are very actually correlated with the nucleus segmentation and detection on pathology slides. So that's why I will explain just one example at the end of my presentation. Okay, so after that brief introduction, let me now give you a very brief account of digital pathology, and let us start with the major technological quantum leaps we have observed in human history, and its mapping into the technological evolution of pathology. As you all know, in human history, we have certain time periods that dramatically change our lives, and it was the third industrial revolution that put computers into our lives. And now we're at the beginning of a new industrial revolution, Industry 4.0, which is in the process of making intelligent computer systems integral and indispensable part of our modern society. Now we have started facing the intelligence systems in every aspect of our lives, including medicine in general and in pathology in particular. Following these technological breakthroughs, we may consider a pathway in 3 stages towards the digital transformation in pathology. Digitization can be considered as converting glass slides into a digital format, whereas the digitalization is about converting processes related to pathology practice into their digital equivalents. And for example, you may consider telepathology systems, or you can consider the use of computers for pathology education, but this does not always mean the digital transformation. In general, digital transformation can be defined as the novel use of digital technologies to create new business models, optimize processes, and automate systems for system-level restructuring of businesses, industries, societies. And from a perspective of pathology, we may, for example, envision the use of automated systems or decision-supported systems in the common practice of pathology. So we are not there yet, but we are all working on designing and implementing algorithms towards the goal of realizing digital transformation in pathology. So now let me continue with our projects in my research lab. So we have three main ongoing projects right now on digital pathology. So the first one and the most recent one is analyzing pancreatic neuroendocrine tumors or PANNETs on whole slide images. This project will have two parts. First, segmentation of PANNET regions on a whole slide, and then characterizing these regions based on their cell and tissue characteristics. So we already obtained some preliminary results for the first part. So it is very exciting for us. And I would like to share just a single slide to show you this work in progress. So that is our design. That's an end-to-end design that outputs the patch level classifications for a given slide, training a convolutional neural network classifier. So that is our preliminary results, one of the preliminary results on a test slide. So these red dots correspond to the identified PANNETs. So we found it, our pathologists found it very promising. So we are now in the process of making new designs, new convolutional neural network designs to make this classification more accurate. Then we will continue with some cell segmentation and cell characterization studies on the identified regions. And our second project, that is also a recent project, is identifying homologous recombination deficiency in pathology slides. Here, the aim is to discover cell characteristics associated with homologous recombination deficiency, and it requires segmenting the cells and characterizing the cells. And the last project is detecting tumor buds in H&E stained tissues. So that is a joint work with Case Western Reserve University. And in all these projects, we need segmentation models. We need effective and accurate segmentation models. And these models should achieve segmentation at different levels, at the tissue level, at the patch level, at the slide level, at the nucleus level. In general, segmenting the pathology images has its own challenges. First of all, these images may contain large variants due to their nature or due to the nature of the problem, due to the nature of the application. Additionally, there could be some variance, noise, and artifacts because of using non-standard procedures in preparing the samples or some non-ideal condition in experimental setup and imaging. So that's why in order to design a neural network, accurate neural network, accurate deep learning model, we need large annotated data sets. However, as you all know, it is very hard to get the annotations. So first of all, annotation necessitates domain-specific knowledge. Second, we may have some inconsistencies in the annotations. So there may be no consensus among annotators, or sometimes there could be inconsistencies in the annotations of the same annotator. So these are all problems. Most importantly, for segmentation studies, we need pixel level annotations, and getting such kind of annotations takes lots of time. So that's why in this domain, we have our data sets are small and much smaller than those that are used in other computer vision tasks. So we need to design our algorithms that also work with small data sets. And I believe that that is the most important challenge in this domain for digital pathology. Of course, there could be other challenges according to the application. So for example, we may face the class imbalance problem for the application of detecting tumor buds, because the number of tumor bud pixels is much smaller than the number of non-tumor pixels. Or as another example, for instance segmentation problem, we may encounter the difficulty of identifying boundary pixels of the touching instances. So such issues should be addressed to develop accurate segmentation models. And in my research group, we focus on developing such kind of deep learning models. And our models were based on designing new network architectures as well as defining new loss functions. So today, I will give you 4 examples of our models, and I will start with a model. So the first one is the multi-stage learning model based on adaptive boosting for gland segmentation. Actually, that was the thesis of Gözde. And here I will start with the motivation, giving you the motivations behind this model. So as we know, it is difficult for a segmentation model, for a dense prediction model, to learn some group of pixels. As we mentioned, for instance segmentation, a typical group corresponds to boundary points. In order to learn these boundary points sufficiently by a segmentation model, there could be different approaches. So there are 2 main approaches. So the first approach relies on designing multitask networks with an additional task of boundary prediction. So here the network is trained also to minimize the loss defined on this additional task, which means that it helps increasing the accuracy of the overall system for boundary prediction. And the second approach relies on increasing the relative loss contributions of the boundary pixels. So this is like defining a weighted loss function. So both of these approaches led to promising results for boundary prediction, for successful boundary predictions, but there may exist other groups of hard-to-learn pixels. So for example, due to the density differences inside the gland and outside the gland tissue and the connective tissue, the fixation and sectioning procedures may result in large white artifacts outside the gland, as you see here, as you see here, here, and here. So our model, our proposed model, provides a scalable solution for also learning such hard-to-learn pixel. So we don't need to specify what to attend beforehand, but our model will learn what to attend during the training step. So this model designs a multi-stage network and introduces a new loss adjustment mechanism for a dense prediction model. In this multi-stage network, each stage inputs an image, this input image, and a probability map from the previous stage, adjusts its loss function, and outputs a new probability map for the next stage. For example, stage 2 takes this probability map as an input, and in this probability map, we have incorrect predictions for the boundary pixels as well as this the bottom of this gland. So it takes this probability map and it calculates a weight map, giving more attention, paying more importance on these pixels, and makes the change in its loss function, and then outputs a new probability map for the next stage. And as you see here, we have now better predictions for these incorrectly predicted pixels. Since this network adaptively changes the loss functions from one stage to another, this network learns what to attend at each step directly on image data without necessitating prior definition about what to attend. So here are some calculations. This is the weighted loss function. So C is defined, the loss weight C is defined for each pixel P and for each stage N, and it is multiplied with a factor beta. This beta decreases for correctly predicted pixels. Here we have an absolute value, which should be a positive value, so that it is 1 minus that positive value, and it decreases for incorrectly predicted pixels. So here are some results, some quantitative and visual results. So we obtain good results for segmenting normal and cancerous glands, and our visual results illustrated that we have this proposed model is effective in predicting better boundaries, good boundary, it has good boundary predictions, and also it is effective in eliminating the, for example, this large white artifacts, as you see in the results of our model. So, okay, Simon, you raise your hands.
Yes, I have. I thought I'd ask a quick question if that's okay.
Sure.
So when determining this weight map, so I'm guessing that's calculated by looking at the output probability map and also the ground truth.
It is actually that is the factor. So it just uses the predicted map, but of course you need to know whether it is correct or not. So you need to know the gold standard map, but it is done in the training. So the gold standard maps and the predictions are available. So you can do the math while training your network in the training part.
Okay, sure. Then at test time, you just have one single pass through the network, do you?
Yes. So at the test time, you don't need to adjust the weights, because at the test time, you don't need the loss function, because you don't, you're not minimizing a loss function, which means that you don't need to use this loss weights.
Okay, sure. So in the previous, I think one of your previous slides, you had this like sequential figure. Okay. So I guess at test time, you won't have that sequential process anymore, will you?
Okay. Yes, yes, we should. Okay, but here, okay, so we take the input image, that's a null map. So the stage one makes the calculation, and here actually we need. It is not like using this let me say weight map for the pixels for this C map. So that's why at the test time you don't need to know whether the prediction is correct or not. You're just using some null maps, for example, if you're implementing it in a deep neural network library.
Okay, perfect. Thank you.
Sure, no problem. Okay, let me continue with the next model. So this is the model that we propose to, okay, that we propose for, let me put, okay. So that is the model that we propose to better preserve shapes in a segmentation network. So let me give you the motivation first. So as you all know, training of a segmentation network, a dense prediction network, for example, a UNet architecture, also relies on minimizing a loss function. So this loss function is typically defined by defining the loss of each pixel separately and by aggregating these pixel-wise losses, and also you can give weights to contribution of each pixel to the loss function. So here's an example that's an weighted categorical cross entropy, and as you see here, it is very common to define the loss function of a pixel, for example, of a pixel I, on its true and predicted values. So here, true value, predicted value, but we mostly don't consider the predictions of the other pixels when we are defining the loss of that particular pixel. And also it is very common to aggregate the pixel-wise losses by averaging or summing without considering spatial relations between the predictions of different pixels. So such kind of loss functions, that's why such kind of loss functions do not, or let me say, may not sufficiently impose a network to learn a particular shape, because we are not using the spatial relations between the predictions, and we are not using the predictions obtained on the other pixels to define the pixel of, to define the loss of a particular pixel. However, this could be important for some applications. For example, for segmenting nuclei, which shows similar morphological characteristics due to their biological natures, we may need such kind of shape-preserving loss functions. So to address this problem, in this work, we define a new shape-preserving loss function. So we call it a Fourier loss. And actually, the Fourier loss is a weighted cross entropy where the weights are calculated as follows. So these are the weights and they are inversely proportional. They are calculated inversely proportional to the similarity between the shape of segmented objects that pixels belong to and the shape priors estimated on the ground truth objects. So we are making that calculation at the end of each epoch for the current segmented objects and considering the shape priors estimated on the ground truth objects. And in order to quantify the shape of an object, either the shape of a segmented object or the shape of a ground truth object, we propose to use the distance to center function. So it is the psi function. So it is defined on the arc length. So that is the arc length from the origin to the corresponding point on the object contour. And after, for example, this function gives you a constant function for a circle because the radius is always the same for the contour points of a circle. And after defining this function, we propose to expand it in a Fourier series and use the harmonic amplitudes of its Fourier coefficients as the Fourier descriptors of the object. And after calculating those Fourier descriptors, then we calculate these pixel weights on the new space of these Fourier descriptors. So these are the calculations for Fourier descriptors. So we are going to use the first n harmonic amplitudes of the Fourier coefficients. And after making that calculation, we calculate a dissimilarity metric of each segmented object at the end of each iteration, at the end of each epoch in the training. And this dissimilarity metric is defined as the Mahalanobis distance from the Fourier descriptors of that segmented object to the shape prior estimated for its class. So that is the dissimilarity metric. This FD is the set of the Fourier descriptors of a segmented object O, and we assume that the shape priors of each object follows a Gaussian distribution, and it is defined on the selected Fourier descriptor space. So we did the calculations, we did the estimations of the mean vector and the covariance matrix on the training set, on the ground truth objects of the training set. And this gives us the dissimilarity metric. So we want to minimize it. And we are using this distance metric to define the weights for the pixels. So we find the pixels belonging to that particular object, and we use this distance metric for all pixels belonging to that object. And that is our weighted cross entropy, and the weights are calculated using this dissimilarity metric, this distance metric, and that is the calculation. So for true negative pixels, we are just using a unit weight, but for the true positive pixels, so it is here, we calculated that weight according to the dissimilarity metric. And we are using a maximum value of a dissimilarity metric for all false positives and false negatives. So here are some results. Here are some visual results. So we tested the algorithm for the gland segmentation as well as for the cell segmentation, for the nucleus segmentation in pathology slides and also in fluorescence images. And that is the ground truth. These are the results obtained when a standard weighted cross entropy is used. And these are the results when the Fourier loss is used. And we observed that we obtain better boundary estimations, and also we obtain better shapes when we are using that Fourier loss. And we are also working on designing another model. So I would like to show you our most recent model. And this design uses Fourier descriptors, but this time to design a new shape-preserving network. So this time it proposes to construct a cascaded network in which we estimate the Fourier descriptors from an original image in order to represent the shape-based information, the prior shape information. Then these estimations are used along with the OCT image, along with the original image, to reconstruct the segmentation map. So we tested this model on a segmentation problem from another domain. So it is the Henle's fiber layer segmentation. It is one of the layers in retina, and this segmentation was achieved in optical coherence tomography images. So I just wanted to show you that slide such that we could use such kind of shape-preserving networks or shape-preserving loss functions in order to obtain better results. Simon.
I hope you don't mind me asking these questions, by the way. Yeah, just based on your results for instance segmentation.
Sure.
So quite often when using a network like UNet, you might use a weighted loss function where you have more weight between neighboring objects.
Yeah.
So I was just wondering whether you combined that kind of loss function with your Fourier descriptor based loss function as well.
Yes, you're right. So here, okay, let me come to that part. So we are defining the loss phase with respect to this criteria, but of course you can combine different criteria in one. So most probably you will obtain better results. So that is what I expect. And actually there are lots of things we can do. So I believe that once you play with the loss functions, and once you know, actually, this will be my last words for that presentation. But if you have some prior knowledge and if you know how to represent, how to quantify that prior knowledge in math, I believe that you can define much more successful networks for a given problem. But most probably such kind of networks could be designed for a particular problem. So for example, here we know that we have some prior information about the shape of nuclei. So it is obvious, or here I showed you another example. So actually we have some information about that shape. Okay, so if that is the case, I believe that you can combine different factors to define a loss function, and it will definitely improve the results. So most probably if we combined more factors in that loss function, we would obtain better results. So okay, it's a very nice comment. So yes, that's true. That's right.
Thank you.
Okay, so let me quickly show you the results, just two exemplary test images from this OCT data set. So we realized that we observed that we obtained very good results for that segmentation, and we did some quantitative comparisons, and we observed that we improve the results very much. Actually, maybe I need to say that if you are using the standard OCTs, so that's the standard procedure when you're getting your retinal image. So if that is the case, it is very hard for the ophthalmologist to draw this, to annotate this layer. And in order to do that, they need to use directional OCTs. So it is another imaging technique. So they need to take the image of the retina by giving the beam from different directions. So here we observed that by using such kind of network, shape preserving network, we can achieve the results of the directional OCTs by just using the standard OCT imaging. So that is a very nice improvement for us. Okay, any questions, any comments? Okay, now let me continue with the third model. So that is for semantic tissue segmentation. So this model introduces a new embedding and proposes to learn it from an original image by a generative adversarial network. So this model, this embedding, generates a new output map by combining the input image and the annotated map. So for each segmentation label, for example, for the green label here, it brightens the pixels falling in the region of that label, and it darkens the other pixels according to these equations. And as a result, it combines in that output map, it combines semantic context features and image features, and it combines it in a single output map, and it learns both of them at the same time because we have just a single output map. And that's why their joint learning provides a regularization effect in training, and as a result, it improves the segmentation result in tissue segmentation. So here's one example. So that is our original image. So we have the normal region on the right-hand side, and we have some cancerous part on the left-hand side. And for the normal segmentation label, we have such kind of representation calculated using the annotations, using the gold standard. And we train a generative adversarial network to estimate this map from the input image, and that is the estimation. And once you get the estimations, you can simply apply, you can use a thresholding in order, for example, to find the normal regions on an image. And we tested our model on 3 different data sets containing H&E stained tissues. The first one is our in-house colon data set. So we observed that we obtain good results, we obtain good segmentation results. And also we applied the same algorithm, we tested our model on 2 publicly available data sets, which are epithelium and tubule data sets. And these are the results for this 2 data sets. And that is the last model that I would like to mention. So that is the model that we developed for detecting live cells in vitro images. So this model proposes to approach cell detection as a multitask regression problem in which it concurrently learns 2 distance maps. So the first one is the inner distance. So it is learned in regard to the main cell detection task. So as illustrated here, we have higher values at the cell centers, and we have the outer distance. So this distance is defined to encode cell morphologies. As you see in this example, it gives you a skeleton-like representation for each image, and these are the equations. And we learn these distance maps from an input image by constructing a multitask neural network in this multitask network, we have a shared encoder to learn feature representations, to learn shared feature representations, and then we have 2 decoders, each of which is learning how to estimate its corresponding distance map from the shared feature representation. And since we are learning all of the weights at the same time, it helps better learning the weights. It helps avoid overfitting. And these are some results. So these are the results obtained on 3 different cell lines. These are the vision results. So we observed that we had better results, we had better detection results, and these are the F-score metrics obtained on the test sets. Okay, so as the last remark, so that is the end of the explanation of the models, and as the last remarks, digital pathology emerges as a new field thanks to the recent technological developments, and in this new field, it is very important to devise robust computational image analysis tools. In these tools, the segmentation step is very important because it is most of the time, it is the first step. And deep learning has shown great promise to develop very effective segmentation algorithms. However, training those deep learning models usually necessitates large annotated data sets, which are unfortunately available. Thus, I believe that it is very important to devise deep learning models with additional features. Moreover, I believe that we have an important advantage here, as I mentioned you before. We mostly have prior information about an application of interest. For example, we know prior shape knowledge on cells or prior knowledge on cell distribution in a tissue. So I believe that incorporating such kind of information to the network design may greatly help tackle the problem of having small annotated data sets. So I believe that there are lots of things to do here. And again, I believe that we will see the widespread use of such kind of technologies in common practice of pathology, I believe, in the coming decades. So this concludes my talk, and thank you very much for your attention.
Thank you very much. Fantastic talk, Çiğdem. Really, really interesting. So I think we're going to have a few questions.
Sure.
If you're still okay to answer some of those.
Yes, please. I will be happy to take the questions.
Okay, brilliant. So I'll start off with a couple, and then anybody on the call that has any questions, please feel free to raise your hand or type in the chat. So, of course, you very well explained different methods for segmentation-based approaches in microscopy, mainly. And you also spoke about when you're also provided with limited data. So do you think some of these methods, such as your weighted loss functions, are especially beneficial when you're presented with those limited data scenarios?
I believe the short answer is yes. So when you're working with millions of images, maybe your network can learn such kind of additional information automatically from the data if you had millions of data. So of course, it is not a possibility in digital pathology. Actually, it is not a possibility in any medical image data set. So I believe that there are some patterns, there are some information specific to the application domain. So if you know these spatial things, if you know this prior knowledge, I believe that it helps the network to better learn even with a limited data set. So actually, that is what the clinicians do most of the time. They have some idea, they have some knowledge about what they are looking at. So if we can somehow incorporate such kind of things into the network design, I believe that they will be more successful even with a small data set.
So we developed an approach a few years ago where we were working with limited data. So I think our data set was only comprising of around 30 images,
Okay.
30 very small visual fields. And we developed a nuclear segmentation model that was, so there was a loss function we created that was sensitive to the hematoxylin content. And we found that it worked especially well when we were presented with that limited data set. So maybe that's the sort of finding that you've also found.
It is not a surprising thing for me. So it is what I expected, because there are all like we have that information. So just hiding that information from the network, it might be useful for the cases if you have loss of data, but that is not the case for digital pathology.
And how do you get hold of your data? Do you mainly work with public data sets, or do you have a partner in hospital?
Actually, most of the time I have worked my own data set. So I had collaboration. I have still collaboration with another university when I was at Big Kent University. But now I am working with the pathologists here at Koç University, and they are interested in what we are doing, and they are providing us some data. So we can access the data right now. So for example, I mentioned these research, not this research. I mentioned these projects. So these are the two of them. The first two are very recent projects, but we are very exciting. So for example, for the second one, actually, we will obtain some genetic data as well, and we will analyze the mutations. So we have very good collaborators here that who can provide us some data together with the related information. So I believe that I am very lucky to be here.
Great. So we have one question online from Mustafa.
Okay.
So I'm going to read out the whole thing, if you don't mind. So Mustafa said, thanks for the great presentation. Really enjoyed the idea of Fourier loss function to enforce some shape prior knowledge. I understand it's applied on each instance in the ground truth. However, I was not able to understand how the corresponding instance from the binary prediction map is extracted. So if you can answer that question first, then there's a follow-up afterwards.
I believe that I got the question. So let me, okay, it is not here, but anyway, so you have you're not matching the segmented objects with the ground truth, but for the ground truth objects, for all of the ground truth objects, you are estimating a distribution. So here we assume that they follow Gaussian, so they have these Fourier descriptors, have the mean vector and some covariance matrix, so you know how they distribute. For example, you have such kind of like distribution if you have a single one-dimensional data, one-dimensional Fourier descriptor, and now that is what you know. And now you have the estimations. These estimations could be anywhere. So you're not trying to match the segmented regions with the corresponding ground truths, but you're calculating the Fourier descriptors of the segmented object, and then you're calculating this dissimilarity metric. So for example, suppose that is the gold standard, and suppose that somehow you found a, let me say, object here or object here. So you calculated the Fourier descriptor of that object, and then you calculate how similarities to a ground truth object. So suppose that you have found one object here, it does not overlap anything, okay? So still you're making the calculation, and then you're calculating the dissimilarity metric, But here, if it does not overlap anything, you're not using this dissimilarity measure. You're not using that dissimilarity metric of an object in the definition of any of the pixels, because there is no overlap. So here, if you identify an object here, it is false positive. So if it is false positive, it is penalized with that weight value. But if it overlaps, so if we have such kind of overlaps for the overlapping pixels, we are using the dissimilarity of the segmented objects that the pixel corresponds to, that the pixel belongs to.
Okay, thank you.
I'm not sure if it is clear or not.
I hope that's cleared things up, Mustafa. And he also asked whether the implementation of this loss function is available.
I believe that it is available somewhere. So it is the implementation of my student. Maybe you can check that thesis. So it is publicly available. Just Google it, and maybe he put some implementation link. So if it is, you're free to download it. So,
okay, right.
But I could also help you if you're interested in more.
Okay, great, thank you. So I'm also wondering. So you spoke about the GAN-based method for segmentation, which is really interesting. So when would you recommend to use GAN-based segmentation, and when would you say that it's not needed?
So it depends on the application. So here, if you want to keep the image details somehow, so maybe here, I'm not sure if it is here. So we compared it with different approaches. So I don't remember the exact details, but in one approach, we use a multitask design where we estimate the segmentation map as one of the tasks, and we are reconstructing the image as the second task. So it is like such kind of multitask architecture. Most probably that is that multitask architecture. And in that case, it may help. So it depends on the application. But when you put these two information into the same map, we observe that we obtain better results. So if the details of the pixels, if the details of the regions is important to you, most probably you may want to use such kind of approach. But if you have some, let me say, if you have some heterogeneous, for example, because of the noise and artifacts, maybe it can lower your results. So it totally depends on what kind of segmentation problem you're dealing with.
Okay, great. So a lot of the approaches, well, most of the approaches that you spoke about today are segmentation based, right? So when would you choose to use a segmentation-based method for analysis rather than, let's say, for example, a patch-based classification method?
So again, it depends on what kind of resolution that you're interested in. So I gave that example. So it is just from a work in progress. But if you want to, for example, analyze the whole slide, of course, you may want to use a segmentation model. But if the speed is important, and also if you are processing the identified regions later once more, you may want to go with the pixel level, not pixel level, patch level classification. So here, that is not our final aim. So we are not using the exact boundaries here, but after finding the, for example, in this case, PANGNet regions, these red dots, we may want to make further analysis. So for example, we may want to call some segmentation algorithms, on the identified patch. So if you need rough segmentations, let me say, you may go with the patch level classification.
I guess as well, this means that you wouldn't have to spend as long annotating precise segmentation boundaries as well, would you?
For that one, so in that case, of course, so it depends on, so here, of course, that is the first step after finding these regions. So now we are in the process of getting more annotated data. So now we have 20 slides, 20 annotated slides, but we need more slides. So after training such kind of classifier for a patch level classification, we may ask them to make more detailed annotations. So that could be a possibility, but these possibilities should be assessed after getting some results, because sometimes you can spend too much time for the annotation, and sometimes it may not be that useful according to what you're doing. So here our aim is to get some quick results, some preliminary results to understand whether the model is working or not. And of course, if that is the case, if the doctors are interested in getting more details on the boundaries, of course, we need finer annotations. And in that case, for example, we may want to go with a dense prediction model where we are making a pixel level estimations.
Okay, makes sense. Thank you. Has anybody online got any further questions?
Just one question.
Yeah, Mustafa, please go ahead. There was a bit of background noise, hopefully.
Yeah, I'm so sorry. It was,
yeah, that's fine.
That also is using this began. So thank you, Çiğdem, for the great presentation. So
thank you very much for attending.
Yeah, I really enjoyed it. So for GAN-based segmentation, so did I get it right that you use intensity maps, just greatest scale inputs to the network, or am I wrong?
So it is okay. So it is here. So the input map is a 3-channel map, RGB image. And we are, so in that case, we have 5 segmentation labels. So suppose that is 4, because we have 4 of them here. So suppose that we have 4 segmentation labels. So the 4th one is not here. So for each segmentation label, we are generating a map. So the new output map is a 4-channel, for example, output map. So it is like a regression problem for 4 channels. So your aim is to estimate those 4 channels from a 3-channel input image by using a actually conditional generative adversarial network.
Very well, thank you.
Okay, are there any final questions? I believe not. So I think we can thank you for a final time, Çiğdem. Really enjoyed your presentation. I'm sure I'm speaking on behalf of everybody here. And
thank you very much for the invitation.
No problem. We really enjoyed it.
I'm very happy to meet you in person as well.
And you. So hopefully we can meet at some point in the future in person.
I hope so. So I will be very happy to host you here if you want.
Lovely.
So, if you want to visit Istanbul and Koç University, maybe after COVID, I don't know, but you're always welcome to visit us.
Brilliant. Thank you again. See you then.
See you. Bye-bye.